Good evening all. Great to see such a good number for this December meeting. So first things, put your hands in your pockets. If you can find any Xboxes, portable telephones, blue teeth, robotic balls, HoloLenses, Blackberries or Raspberries, now's the time to turn them to silent. If there's a fire alarm, I think it'd be quite a good idea to leave the building. So, and toilets are outside. So, Andy Alder's jamboree for you tonight. Andy Alder and 4 young Turks. So I've got a very long biography on each speaker, which I've cut short a little bit. So Andy Alder. Andy is the Programme Director for Tideway as part of the Jacobs Programme Management team and is responsible for delivery of all the infrastructure for the project. Before Tideway, of course, all of you will know that Andy was Project Manager for construction of all tunnelling works in the west area of Crossrail. Lee Fisher. Lee is a Project Manager for Tideway, again as part of the Jacobs Programme Management team on the Albert embankment foreshore site. Lee joined the site team earlier this year following 18 months managing third-party asset protection across the Tideway programme. Jonathan Chu. Jonathan works for Lang O'Rourke as a Senior Project Manager on the Blackfriars Bridge foreshore site of the Thames Tideway Central Project in JV with Ferrovial Agreement. Jonathan is a Fellow of the Institution of Civil Engineers and a Fellow of the Chartered Management Institute. Tom Brown. Tom is a Chartered Civil Engineer employed by BAM Nuttall, site agent for the Putney embankment foreshore site on the Thames Tideway West project for the BAM Nuttall Morgan Sindall Balfour Beatty joint venture. Ed Lewis. Ed is a project manager with Jacobs, currently working on Tideway in the delivery of the central section, main tunnels and Kirtling Street Drive site. Ed is a chartered civil engineer with experience in SCL and TBM tunnelling in London, having worked on various aspects of Crossrail and Tideway in design, construction and project delivery roles. So Andy, if you want to take over.
Thank you, Ivor.
I don't know, would you mind sending those out, John? I've forgotten those.
Thank you, Ivor. Good evening, ladies and gentlemen. Thank you for the opportunity to give you an update on the Tideway programme and the work we're doing. So I'm going to be very brief because the main event is the 4 guys there who are going to get into the detail, and that's who you really want to hear from. So this is just a very brief overview of the programme as a kind of recap in case you're not familiar with it. Bit of a quick overview on where we are on the project overall, and then I'm going to hand over to the guys. We've been through the introductions. So I'm sure many of you are familiar with this, so I'll be very brief. But this is what London looked like in the 1850s. All of the tributaries flowed into the River Thames. It was used as basically the sewer system was the River Thames, and people were pulling drinking water out of the River Thames. And there was major cholera problems, a huge public health issue, and something had to be done about it. So Sir Joseph Bazalgette was the city engineer. He undertook a fantastic project, which was to build these interceptor sewers, which intercept the tributaries as they go and carry everything out to the east, to the estuary, and solve the problem. Fantastic piece of work. It's in brilliant condition, but the problem is with capacity. So Sir Joseph Bazalgette designed the scheme at a time when there are 2 million people living in London. He designed it for a capacity of 4 million people. But now there are nearly 9 million, and it's continuing to increase. And the issue is capacity, and particularly in the summer when there are kind of short duration rainstorms. With the amount of hard paving in the city, that the rainfall gets into sewer very quickly, and it reaches capacity, and it overflows into the river in places like this. So these were overflows that were designed into the system as a safety valve, but there's now on average 50 million tonnes of untreated sewage going into the River Thames every year. Because the Thames is tidal, that doesn't flush out of the system very quickly. it goes downstream and comes back upstream, and it can take a couple of months to get out of the estuary. It's harmful to health, and there are people who work on and use the river for leisure purposes, so it's harmful to health. It obviously looks pretty bad for one of the world's greatest cities, and it kills fish. And if you get a sewage plume going into the river, it can have a big effect on the fish population. It can kill fish when they're spawning, and the Thames is a spawning ground for fish in the North Sea. So this is a major problem. But fortunately, we're here to do something about it. So this is a typical shaft on the Tideway project. This is just opposite the London Eye at Victoria. And you can see on the right-hand side is the embankment with the existing Bazalgette sewer there. We're building cofferdams into the river. Typically, we haven't got space to do any other work apart from build into the river. We're then sinking shafts that can connect the sewer system down into our main tunnel. So the sewage, when it's operational, will overflow into the shaft and down into the tunnel. Our tunnel is basically a big storage system, and then when the rainstorm has gone past, it can be pumped out through Beckton Sewage Treatment Plant to stop the sewage going into the river. This slide, I think, is great because it kind of just shows the scale of what we're trying to deal with. You know, these shafts are up to 60 metres deep. You've obviously got the technical difficulties of working in the river, complex ground conditions. You've got stakeholders nearby. We've got transport stakeholders, buildings nearby. We've got the whole range of authorities to work with to get consents. So it is a technically complex job, but organisationally and project delivery-wise, it's complex as well, and that'll come out in the presentations that the four guys are going to give you. End-to-end, the project's 25 kilometres long for the main tunnel. We've got 3 sections of work. West is purple, central in orange, in red, the dark orange, and east in the light orange. And you can see we've also got 2 shorter connection tunnels, the Frogmore connection tunnel in the west and the Greenwich connection tunnel in the east. And when the project's finished, as well as cleaning up the river, because we're building out into the river, we're creating new public realm, again, like this site here opposite the London Eye, where we're creating new public space for the first time in 150 years. Am I supposed to sing? Is there anything we could do about the music? You can hear? Right. So progress. Starting off, progress on health and safety. When we started Tideway, we set out to be what we call transformational in terms of health and safety, and we had a lot of discussion about what do we really mean. And it boiled down to 3 things. One is getting the basics right. The second thing is continuous improvement and trying to learn. And the third thing is bringing best practice in innovation. So we've worked across the programme. There's a whole range of contractors. We've got Balfour Beatty, Morgan, and BAM. We've got Froville and Lang O'Rourke. We've got Costain, Vaughancy, and Bashi, all doing fantastic work on the project, working together. Our starting point was to kind of pull together what is best practice from projects we've all worked on before, and let's get the basics right, things like exclusion zones, how the sites are laid out, what the welfare is like. We then do a lot of work on lessons learned. Yes, of course, we investigate when things don't go quite to plan and get some shared lessons learned on those things, because if something's happening on one site, it's bound to be happening on other sites as well, and it's good to learn. But we also focus on trying to learn from things when they do go well, and 99% of the time things go really well, and we should learn from the stuff that goes well as learning from when things don't go so well. And we also do things like our Right Way in Delivery awards program to really recognise and celebrate and share the innovation and best practice that people are doing every day. So health and safety is in good shape. Obviously, you're only as good as your last 5 minutes, so it's something we can't ever let our guard down on. But our most important thing on progress is the work we're doing on health and safety. In terms of logistics, we made a very conscious decision to put as much logistics off of the road as we can. We're fortunate we got a lot of the sites are on the riverfront, so we can put logistics on the river and taking road transport off of the road Clearly that brings environmental benefits in terms of air quality, and it brings health and safety benefits in terms of reducing risk to pedestrians and cyclists. So we've put, as you see on the slide there, over 2 million tonnes of material has been moved by river already on the project, and that's 200,000 lorries that we've taken off the road and on the river. Clearly there are health and safety risks around operating barges on the River Thames, and there's been also a lot of great work done on enhancing the training and competence and certification of the crews on the river, and helping the river industry to develop as well. In terms of progress, we're making great progress across the project. Our first main TBM drive has been complete. We've got more than 10 kilometres of the 25 kilometres is complete. The Frogmore Connection Tunnel has got 2 drives, and the first of those is complete. So in all, we've got 6 TBMs on the project, 4 of which are either in the ground or have completed, and 2 of which are going to arrive on site early next year. And then in terms of the shafts, we've got 23 shafts. Of those, 21 are at various stages of progress, and 15 are at full depth. And as of tomorrow, 15 of those will have their shaft-based slabs in. So again, we've made really good progress on the challenging work of getting the shafts excavated through some pretty difficult ground conditions and in some quite complex locations, which the guys will talk about. So really, that's the kind of overview. I'm going to hand over. We've got presentations from Lee and John and Tom on Alder and Putney and Blackfriars sites to give you a flavour of what's going on there, and then Ed's going to talk about the TBM drives and what we're doing on the TBMs, and then I'll come back and just do a very quick wrap up. Lee.
Good evening. Hi, I'm Lee Fisher, Introduced Project Manager for Jacobs on the Alder embankment site. Just a little overview of the site there. First of all, where is Alder embankment? Many people might know it, but it's just a few hundred metres south of where we are now. The site's down by Vauxhall Bridge, and you're on the south bank of the river. I think this photo the photo shows where we are in relation to the land. We're all out in the river. We've got very little space on land to actually do any of the work we're delivering here, which makes it a real challenge, and as Andy was saying, the marine logistics become key. I put this slide up to sort of pick up on some of the stakeholders we've got. Obviously, being in the river, we have quite a few consents with the Port of London Authority, Environment Agency. You can just see the river wall in the background there that we're amending. The Marine Maritime Organisation as well. The bridge here that the photo is taken on is Vauxhall Bridge, so one of TfL's key assets in the area. Behind, you may recognise a building from James Bond films, which features as MI6, so we have some specific security arrangements around that. And then the buildings in the background are owned by the Duchy of Cornwall, which is Prince Charles's trust. So some challenging stakeholders to deal with. The button's not working. I'll try that again. There you go. I went backwards. What are we doing at Alder embankment? We're picking up 2 combined sewer outfalls, one either side of Vauxhall Bridge. So at the top of this picture, you can just make out Vauxhall Bridge there. The Brixton sewer runs on one side and the Clapham outfalls to the other. We collect the sewage from both of those. We take them into the interception chamber, which is the green structure on the diagram. From there, potentially at high flows, we've still got an overflow into the river if the sewer is not available for any reason. But in typical situations, the sewage will then drop down through cascades in the green interception chamber, drop into the purple connection tunnel, flow along into the drop shaft where it'll go down a vortex into a connection tunnel, which is only 10 metres long then, into the main Tideway tunnel at the bottom of the diagram. To construct it, we need quite large cofferdams. As you can see, cofferdam 1 is labelled up there around our drop shaft. It's about 2,500 metres squared. And then cofferdam 2 is up at the top near Vauxhall Bridge. And we've also got a third cofferdam, which I'll cover as well in a minute. So this is just a picture of cofferdam 1 that was being installed. This is formed from twin wall Sheet piles, it's been backfilled in the middle with ties across between them. It's quite a substantial structure. This is partly because as we do the works, we have to remove parts of the existing river wall. And so to ensure that London isn't at risk of flooding, we need to replace that river wall by a substantial structure. So our cofferdam becomes the temporary river wall for London. It also needs to be able to deal with ship impact protection. If a vessel became loose or was out of control and struck the cofferdam, we'd want to make sure, again, that the flood risk is managed, but also the safety of our workforce on site is controlled. And then this is during construction, so you can see some of the marine vessels that were used during the construction of that piece of the work. Cofferdam 2 is slightly different construction. There isn't the space here. We've got no access at all. We do have some road access into Cofferdam 1, but here we have nothing. So we're just next to the Thames path. You can see the existing river wall in the background. It's been excavated away in front of it. And the cofferdam is made up of a combi wall pile system. So you've got large tubular piles with sheet piles in between it. The retained height of that is about 8 metres. So these are quite substantial structures. And in this case, the ship impact protection isn't provided by that structure itself. It's actually secondary structures out from the river wall, from the cofferdam. So we've got some additional piles in there, and as well at this stage in the progress, the jack-up barge that's visible, the green jack-up barge, forms part of the ship impact protection. And that's a key part of managing the risks as we go through it, ensuring we've got that protection. Just some stats on those first 2 cofferdams. We started work in 2018 on those and finished them earlier this year. But you get a good idea of the large marine fleet again that was used to install those, a mixture of jack-up barges, flat-top barges and various support vessels. The team adopted some best practice to try and reduce noise, because a lot of those piles we've vibrated in, or they're driven in with impact piling. We have buildings which are immediately adjacent to the work, and we installed significant amounts of secondary glazing on one of them with air handling units to manage and mitigate that noise level. But to achieve the best practical means for controlling noise, we also used these cameras that pick up where the hotspots for the noise are on the various pieces of plant, and then the mitigation can be developed around where those hotspots are, so you can put shrouding or other details around it. For example, in the diagram at the bottom, it shows a real hotspot of noise from one particular area of that bit of plant. Not something we could do about immediately, but potentially the manufacturer of that bit of plant could amend what they're doing for future projects. Our third cofferdam isn't yet constructed. We mobilised just last month, and there's a picture of it just there. It's much smaller, the current scheme that we're doing. It's the other side of Vauxhall Bridge. So again, we have very limited access to this area. And there was a real challenge that was faced during the design development. So if I just show this out here, the red line was the original cofferdam proposal. You can see there that the cofferdam used bridge pier of Vauxhall Bridge as part of the cofferdam, which presents some challenges in convincing Transport for London that's an acceptable approach. But also, again, this would have been a large structure, so we would have had piling within about 3 metres of the Victoria line. London Underground had a number of concerns around that, which we would have had to address, and it would have been a large amount of night working and significant noise at night as well to install some of those piles. So the team at Frovia and Lang O'Rourke, who were delivering this, came up with an alternative. And they adopted a tunnel technique, so very suitable for today. They shrunk the cofferdam down to just a 10-metre square, which you can see there. And then underneath Vauxhall Bridge, they're going to install 2 lines of sheet piles, a twin wall arrangement, and they'll form a cut-off wall. The alluvium and made ground on that will be removed, replaced with lean mix concrete. Then a capping slab put on to watertight that section, and then we'll be doing a pipe jack beneath that part of Vauxhall Bridge to connect up cofferdam 3 here to the rest of the works in the interception chamber. So there's a really good development of the design as we progressed. Moving on then to the shafts and the tunnelling works. Here we've got an image from in the shaft. It just shows one of the challenges we've got. So you can see the secant piles coming up out of the ground. The top half of the tunnel, about 26 metres, is secant piles. And then below that, I've done my numbers wrong here. I said 15 metres sprayed concrete lining. It's 21 metres of sprayed concrete lining below those piles. So we've gone down quite a substantial depth, 50 metres in total. And we're only about 4 metres away from the nearest building. We go deeper than the foundations for that building, which is Camelford House, which you can see in the picture there. And a lot of work was again done to check that we were safe to excavate and model the impact on that. And the impact that we've had on that building, having undertaken the works now, has been significantly less than was predicted. So it's a really good result. And the team that delivered the SCL works did really well with that. It's just some details on the geology we took the shaft through. The purple band is the London clay. So the secant piles went into that, and then the SCL work started below that section. We went very deep, so where most pieces of work in London have stayed in the London clay, we've then gone down underneath into the Lambeth group to get down to the main tunnel level. Because of that, there are some sand lenses in some of those deeper sections, and they needed to be dewatered. So there were surface level dewatering arrays installed, but also when we got down to a suitable level, there were vacuum pumps installed within the shaft that drew down some of the sand channels, took the water out of there. Unfortunately, as we continued to excavate, the team discovered a perched water table. There's a band of clay which sealed off the sand channel halfway through, and they dealt fantastically by draining out that extra perched water table, modifying the SCL works as they went down, and progressed through that with very little difficulty in the end, but it could have been a real challenge having discovered an unexpected bit of formation in there. We've also included there the dashboard, which just shows some of the monitoring details. We have a huge amount of monitoring on the project, but that's from WJ Dewatering. That's the dashboard that shows us how well the dewatering system's performing, which is reviewed every day. It's a shot of the connection tunnel where it was still being constructed. It looks a little different now, the secondary lining's going in. But it's relatively small, 3.9 metres diameter, and you can see that the plant there fills up the tunnel pretty much. So one of the real challenges with that was making sure that we had people-plant interface controlled properly. There's a lot of discussion whether we should have walkways and other features, but we reviewed the risks carefully, and actually having a full exclusion zone for people in being out of the tunnel or just at the face when any vehicles were moving was the way forward, because it was just too constrained to do anything other than that. But this work was delivered 6 weeks ahead of programme. The team did a great job in delivering that. Had some really good innovations again that the team came up with in developing the work. This canty deck, you see them quite commonly on high-rise buildings. It was adapted for use in the tunnel, so what it's hanging out of there is the portal for the connection tunnel. So the tunnel was built, we installed the canty deck there, and then continued shaft excavation with that cantilevering out from the shaft. And that meant that the works to install the waterproofing and the secondary lining could progress in parallel with the shaft excavation. And again, a fantastic saving on programme that's delivered. And I find a bit of best practice. Lifting in these tight shafts has been a real challenge, ensuring that everyone's safe, having heavy loads over people. So there's some really good controls have been developed and shared, and they're very simple to make sure that it's easily communicated when there's lifts going on who should be excluded from various areas. So this is a photo from within the connection tunnel. You can see the canty deck just in front, and then a load being lifted just in front of that. And there's this traffic light control system. Red obviously means you're not allowed out into the excavation, but this has worked really well, and it's meant that people obey the exclusion zones, and it's kept the work safe so far. We've also implemented a clash detection system on the canty deck because it's quite a big structure sticking out into the shaft. It's a risk of being hit by loads. And there's laser beams that detect any movement. And so the crane driver can see any effect, and if he's got a load that's going to clash with the canty deck as he's lifting and lowering the load. The finished scheme, I always think, is somewhat a little disappointing because there's some huge engineering works we're doing at the moment, and it looks absolutely fantastic. But we will be handing back this finished public realm, which is going to be excellent. As Andy said, first new public realm in London for a long time on the river. We've got the two sections here, one on the left and on the right, so a circular section and a slightly larger one on the left. this will be there then at the end of the project, sitting above the shafts, and no one will be aware of all the work that's happened underneath them.
Thank you, Lee. So Blackfriars is one of the most complex and constrained sites on the whole of the Tideway project. And today I'm just going to talk you through two of the more intricate bits of the job. So I'm just going to cover a short amount on the project constraints, then go on to the shaft and the ground treatment works that we've undertaken, and onto the floated culvert, which is currently in construction. So Blackfriars is one of the more central sites of the project. It sits within the City of London, right next to Blackfriars Bridge, and is right up against a listed river wall. Within that river wall is the service subway built by Bazalgette and the lower level sewer, and the service subway contained two large low and medium pressure gas mains that were very sensitive to ground movements. We're also next to Victoria Embankment, which is a major TfL highway. Just north of the embankment is the District and Circle line for London Underground. Then you can see here, you can see there the Waterloo and City line. That's 6 meters below the riverbed level and straight through our site. The bridge itself is listed. And just to make all of that a bit more fun, the purpose of Blackfriars is to pick up two sewers, one of which is the Fleet sewer, which outfalls underneath Blackfriars Bridge. There. And means that you can't get any cranes to it or get anything under it, and the distance between low or high tide and the river and the deck of the bridge is pretty negligible. And then the second sewer that we're picking up is the lower level sewer, which will be a side entry there into the listed river wall. So, full of constraints, and just to add on to all of that, as Lee had explained with Albert, we're basically building everything out into the river, which has its own constraints. The job itself consists of a large 22-meter internal diameter shaft, 50 meters deep, and then the two culvert structures to connect to the two sewers. So here's an aerial photograph of the site taken in June this year. I had planned on putting another newer aerial photograph in, but the photographers weren't allowed to do that last week due to the NATO summit and restrictions on helicopters flying over Blackfriars, apparently. So what you can see here is the temporary works that were there in the summertime and the piling operations that were going on. So you get a sense of scale from seeing the concrete wagons on the roadway here, and these are 300-ton cranes. So the site's over 250 meters long, and you can see where exactly we're working. Also, this image highlights how we've used marine logistics to our advantage that Andy explained in the introduction. So all material brought to or taken away from the site, including the 300-ton cranes and the large piling rigs, were brought to the site by river. The only material brought to the site by road has been the concrete and some small tools. So that's been a fantastic achievement, and I think one of the differentiators of the project compared to other civil engineering works that I've done before. Here you can see, because I didn't have the new aerial photograph, here you can see where the shaft is located and also where the floated culvert is being constructed, and more about that later. So on to the shaft first. During the tender, the reference design was a diaphragm wall towed right into the chalk strata. And as the project evolved, we worked with Tideway to alter the shaft scheme into a sprayed concrete lining shaft. So the top half of the shaft that you can see on this side of the screen is secant piles towed just into just above the bottom of the London clay, and then it's 25 meters of sprayed concrete lining below that. Now, the main purpose of that and the advantage to the project was to effectively de-link Blackfriars from the tunnelling progress. And why I say that is the diaphragm wall scheme needed the entire diaphragm wall constructed and the shaft excavated to allow the tunnel boring machine to enter the shaft and have a free air intervention. With the scheme as it currently is now, we're actually going to construct the bottom half of the shaft around the completed tunnel after the TBM has passed through Blackfriars, which is programmed to happen in January next year. So that is quite a change, and with that evolution of the design, it needed some quite innovative thinking, which is where the ground treatment works came in. So the ground treatment works comprised of what we ended up calling a belt and braces approach. So the belt, if you like, was quite extensive dewatering. We got chalk wells, Thanet wells, and Lambeth group wells into those strata that you can see on the left-hand side of the screen. That completely surround the shaft. So we've got them on the land side within the existing road, on the twin wall cofferdam, and within the cofferdams themselves. The braces part of the belt and braces approach was probably the more innovative bit, which was to undertake the deepest jet grouting curtain ever done in Europe by Keller's group. And the jet grouting was undertaken to 52 meters deep, with interlocking jet grout columns that effectively replaced the granular strata with jet grouting soilcrete, so that when we were undertaking the shaft excavation using spray concrete lining, we de-risk any loose and running sand. Because the TBM is also coming through into virgin ground and now doesn't have free air to do its intervention in, we also did a jet grout block for the TBM, which is located just here. So there was a slight risk of wet ground that could deravel when the team were going to undertake the intervention next year. And we basically decided that because we were doing such extensive jet grouting for the shaft, we would also undertake that block just to be sure. So you can see this is an image further in the past than the previous one of when we were undertaking the jet grouting operations. So the jet grouting rig is within the cofferdam. The cranes are servicing that operation, and the silos for the cement and all of the mixing equipment are on the top of the twin wall cofferdam here. And all of the liquid arisings from the jet grouting operation were pumped away from the excavation, from the cofferdam, over this bridge onto the barge, and then into the flat top barge via that pipe that is then held by the crane. So we undertook all of that muck away with the support of the Environment Agency and the Port of London Authority, and that was a huge achievement in itself. So in order to validate our jet grouting work, we did a 3D model as the jet grout columns were constructed. So every day at 4 o'clock in the shift review group, we understood the columns that had been constructed that day and understood their position and their verticality tolerance from the equipment on the jet grout rig, and basically plotted out live what we'd done. And we'd had a specification agreed mutually by all parties on the project as what we wanted to achieve with the curtain and the interlock, and then use this 3D model to decide whether we should do any additional columns. In the end, we only needed to do 4 additional columns out of the 131 constructed, because we'd felt that the gaps, there was a risk that those gaps might be too large, and we wanted that full interlock throughout. Just some statistics. So as deep as Nelson's column is a nice one, but more importantly, we did 3 months of 24/7 working without an incident, which is a fantastic achievement by the flow team and Kellers. We were 5 days ahead of program with 40,000 person hours. It's a huge achievement for the team, and really credit to everyone in Kellers and Flow that was involved. And here's a recent photograph of the shaft. We've now half dug the shaft to near the bottom of the secant piles, awaiting for the TBM to come through before we can continue with the spray concrete lining. And you can see on this photo the inlets for the fleet and the lower level culverts that will connect up to the shaft in future. So quickly on to the second part of the presentation, which is the floated culvert. So in this image, you can see the outline of where the floated culvert is being constructed. These are precast planks that we cast off site and brought onto site so that we can build the base slab of the floated culvert off these. So the reason for the floated culvert that I didn't explain when I first brought up this slide is basically you've got the connection to the Fleet sewer is underneath Blackfriars Bridge that I mentioned before. But with the Waterloo and City line being so shallow, and the fact that the reference design had a cofferdam around the bridge pier that then subsequently City of London were not comfortable with, we had to move away from doing anything in the dry and go towards an innovative but what became the only solution, which was to build the culvert in the eastern cofferdam and flood that cofferdam and float it out underneath Blackfriars Bridge, which will be happening by May next year. So here's just a few digital engineering visualizations to show you the sequence of what we're doing. So this first slide is the base slab, which is 3/4 of it, of which is now constructed. We then build up the walls of the culvert. In the meantime, we're undertaking dredging outside of the cofferdam, next to it and underneath the bridge to create the flat level that the floated culvert will go on. The bed that it will go on consists of gravel and then a die-cell product, which is effectively precast concrete. That means that the level inside and outside of the cofferdam is uniform. We then put greedy boards on top of the floated culvert, which is to manage the tide levels for when the floated culvert is floating, because we can't build the entirety of the structure because then it won't float. So none of the roof and parts of the rest of the structure are missing in its temporary state for the float-out operation. We then open up the cofferdam and flood it. We'll do some flotation trials and checks of all of our equipment. And then a bit faint on here, but you can then see the winches, and we'll effectively winch out the structure, just like that, underneath Blackfriars Bridge. So the operation is going to happen over a relatively short period, over a couple of hours period, with brake winches on the back and pulling winches on the front, and other temporary works that we put in place, such as catches on the cofferdam and on the river wall to get the tolerance of the floated culvert correct. Then we reseal the cofferdam around the floated culvert once it's sunk down, and drain the cofferdam, and then start all the in situ works within the eastern cofferdam again to connect the floated bit up to the shaft. Meanwhile, then the in situ section of the floated culvert will be a separate operation where we complete the structure, including the roof, and fully connect it up to the Fleet sewer. Meanwhile, at that time, on the far end of the sewer, at the far end of the culvert, there'll be an opening to allow the live sewerage to flow out east of the works, so nothing comes into the culvert or into the site. To de-risk this operation, we undertook a 1:25 scale model of the whole culvert and its movement in the university in Spain, in Cantabria. So here you can see an image of the full mock-up, and we drove the cofferdam, or floated it out, floated the culvert out of the cofferdam under the bridge successfully numerous times, and we were all happy with that operation. So much so that we got Tideway's project manager to do the actual winching trial in Cantabria, and prove that him without any experience could do that operation safely. So this gave us a really high level of confidence. So here are a couple of pictures of the floated culvert. The one on the left was taken in November when the base slab was in construction, and the one on the right was taken earlier this week. You can see the shutters for the walls going up. So it's a pretty large-scale operation that's 95 meters long, and the culvert will weigh 3,500 tons when it's being floated. And the final slide is similar to Lee's. It's just showing you what the final foreshore structure will look like. So it's a huge new piece of foreshore for London. It will unfortunately cover all the civil engineering hard work that we'll put in over all of those years. But I mean, this will be a fantastic addition to London's riverside. So thank you very much.
Good evening. My name's Tom Brown. I'm the site agent for Putney Embankment Foreshore. As you can see already, we are a serious postage stamp of a site. There's some interesting marine works in there, but I'll focus tonight on the tunnelling elements because you've got to know your audience. So, talking you through the site. So we're looking at Putney Bridge here, which is a Grade 2 listed structure. The existing Bazalgette CSOs come out beneath the bridge arch on the south side. We have an existing slipway where boats are launched down into the Thames, and we are the home of the boat race Starting Stone of Oxford and Cambridge boat race, which occurs in the spring every year. We're also at the tail end of the Thames Clipper service, which runs onto Putney Pier, and then immediately west of here is what's deemed the busiest section of rowing water in the world, with all of the boat clubs that Putney is very famous for. So basically our site area occupies the area between the bridge and the pier. So this is the solution which we've implemented. It differs in a number of ways from the original design. We worked with a contractor called Waldenberg who optimised a number of elements of the design and also responsible for substantial portions of the construction. The section in green is the only area which remains visible after the project is gone. So you can see that all the other structures are temporary, quite significant, and are all removed again at the end of the project. As you can see on the right, the existing CSOs come through there. They then enter into a tunnel, head west through a connection culvert tunnel or high-level tunnel, into the valve chamber, which is the rectangular structure, through into the shaft, down 36 metres in a 6-metre internal diameter shaft, and then out 43 metres in a 2.2 internal diameter tunnel out to the main tunnel drive. So this is the same image again in 3D, so it gives you some idea of what we're looking at here. As you can see, the CSOs fall into the shoulder of the tunnel there and then travel across, similar to John's work, very limited access beneath the bridge. Indeed, the curve and the spring of the arch is covered at high tide, and the whole site has a sort of 6 metre tidal range. If you look at the further image, the whole site is built out into the river, and we started with a section of pavement about 5 metres wide and 30 metres long, and built out from there. So from the two structures you can see within the piled structure, there's a large rectangular structure which is the valve chamber and the drop shaft. Both of these were dug using an in situ caisson method, which is not too common, but I'll tell you why it was a good idea. So this image shows the cutting edge as it was installed on the valve chamber on the left. This is part of Waldenberg's forte. They do a number of these projects and have done them up north and also in their North American division. So this was installed here. We then moved on to building effectively the whole structure above ground, the valve chamber, so a heavily reinforced concrete structure culminating in two concrete pours, one of which is shown on the left, about 210 cube concrete in there. We then had one huge structure, which we then sunk into the ground in 10 working shifts. So absolutely excellent method, one excavator in the bottom and a skip on the end of the hook, and that's how we dug that caisson. So yeah, really simple, has a number of great benefits, no exposed ground, all the ground's beneath your feet, really limiting any risks to the workforce there as well. So on the left you can see that structure sunk down to formation level, so you're looking at about 10 metres deep there with a permanent slab put into place. If you look closely at the left-hand side of that structure, you can also see the eye being formed where the future high-level tunnel eventually leaves the structure. So at this point, I'll move on to the drop shaft, which you can see on the right. So again, an in situ caisson method. Absolutely excellent given the constraints which we have here. So the permanent structure is the inner piled structure, the only permanent works section that goes out into the river. Because of this, the shaft is only 6 metres in internal diameter, so a really challenging environment. But given the methods used and only one person down at the bottom during the excavation sequence, was very manageable. So on top of this, Wallenberg also do a lot of 3D work. They use this in their method statements and for briefing their guys at the sharp end. Really successful. I believe this is probably best in industry right now. Really informative, really easy to understand. And as you can see, the one on the left, it looks very much like what happened on site there, and no problems with quality at all. Similarly, with the image on the right, really explains how that operation goes about from day to day. So as I described, all the muck is below you the whole time. The muck actually kind of peels up towards you. So the muck is probably about 1 metre above the cutting edge at any time. So your risk of losing any bentonite in the annulus is exceedingly low. And all the lubrication is fed through cast-in pipes in the wall of the caisson. So both in the valve chamber and in the drop shaft structure, it is a single pass lining. We do not have any secondary lining. It's been designed to cater for all the requirements that it needs. Obviously a fantastic saving in programme there, and also the exposure which you can potentially put on the guys working at height during that period. So this shows the system again. So the shutters were bespoke but used over and over again. With the valve chamber, we built the whole structure above ground and then sunk it. With the shaft, we worked sequentially, working round and round. So we managed to optimise some of the steel fixing by prefabricating a number of elements. And at peak, we were able to do a 3-day turnaround between excavating, steel fixing, concreting, excavating again. Very efficient method. And as you can see here, the inner shutter could be hydraulically lifted, which immediately provided edge protection for all of the steel fixes working there, and also a bespoke outer shutter with a designed walkway to be able to access the works here as well. The added advantage of this technique is you pour your concrete at ground level, you can strip your shutters, you can see that you're happy with it. Any problems you can see, we didn't have any at all during our works, so you get full visibility of everything before it even goes in the ground. So that's another real good advantage as well. So controlling these structures, so Wallenberg have a number of employees from Oxford University and a research arrangement with them as well. One of their engineers' theses was on the use of this levelling machine, which they came up with. So they had a header tank based at ground level. They then used pressure sensors in the wall, and then tabulated that with a computer coding to create this readable iPad system, which was used by the excavator driver sitting in the base of the shaft. The elements there shown, the single digits were all in millimetres, and we believe it's around 1 to 2 millimetres, 2 millimetres accuracy. Very simple for the driver. Green means dig, red means don't dig. And that kept everything nice and even all the way down. Absolutely fantastic tolerances all the way down and quality throughout. Also limits the amount of time that engineers need to send down to the face, and limits the number of lifting operations required during the works. So that was a real success, and that was used on both the valve chamber and on the drop shaft itself. So moving on to the high-level tunnel, which is in progress as we speak. So if I can work out to use this. Our TBM is working now and is probably somewhere around here, having launched out of the valve chamber in November. So the tunnel is 135 metres long, external diameter of about 3 metres, internal diameter of 2.2, so a very small tunnel in there. Shown again in plan here, you can see a straight, then a slight curve coming round to come perpendicular to the abutment of Putney Bridge. We've had a number of issues into November getting started. So we've had to mobilise a gang last week. We flew in another gang from Canada to go 24-hour working, which has had the desired effect, and we're now progressing very well, and we're hoping to finish early next week, just in time for Christmas, which is good. So in terms of geology for the high-level tunnel, so really challenging in terms of how shallow the tunnel is. In terms of natural ground, you're looking in the region of 2 to 3 meters, well, around 3 meters overburden. So in many areas, the cofferdam has added overburden on top of that. And then the area below the bridge, we've added an additional 1 meter in aggregate to help constrain the ground above the pipe jack there, which has worked successfully. So yeah, here's a few pictures of the TBM coming into place. So we had 1,000-ton crane from Baldwin's come and help us out on that one, and the TBM lifted into place there, so around 70 tons. So that was lifted down into the valve chamber, which is then shown in the middle picture. You can see there, and you can see the jacks there pushing back towards the bridge over there. And the two lines you can see there coming back up the side of the shaft are these slurry lines in there. And then you have a separation plant sitting up at ground level, centrifuge and shaking tables, basically stripping all the material back out, taking the solids out, and then returning the slurry water back to the head of the machine. So on the right you can also see our tunnel pipes, which were made in Northern Ireland in Enniskillen. Absolutely fantastic pipes that are there. They're also a composite lining. So again, we've gone for a single pass solution. So concrete external layer, steel can, and a concrete internal layer. So the elements which are required to finish the tunnel are a welded joint piece to join all the cans together, and then a grouted joint which to work its way through the tunnel. And also the other efficiency here is this pipe is actually the same design used on both tunnels, high level and low level. Okay, so here's our geology for the low-level tunnel. This is an old drawing, so this shows the bell out, which was originally intended in the SCL shaft as it was at tender stage. The caisson has obviously done away with that. So this tunnel is around 43 metres long, uses the same pipes as before, in very competent London clay with about 28 metres overburden in here. So this will be dug with a back actor in the lead pipe, with an open face through there. There's also a fault line there, which is extrapolated from a theoretical position. We don't believe it will be an issue, even if it does arise, given our current design. So here we see the tunnel in cross-section here, again showing the pipes which are there pushing through to the main tunnel. The original design showed a timber heading structure to join into the main tunnel. We're very rapidly considering another option, which includes jacking slightly closer to the main tunnel, and then a much smaller timber solution, which relies on a circular opening rather than a square one. So that's an efficiency we're hoping to push through for February next year. So in terms of our lessons to learn, so some of the best things we've done, I think, are definitely our single pass linings on the caissons, real reduction in working at height there, and the end product, the quality is excellent. Putting another lining over it would be totally unnecessary. I think anyone who visits the site can see the quality of what's there. The composite pipe design, as I've mentioned, doing secondary lining in a small diameter tunnel is exceptionally manual and very difficult. We have a finished lining of 2.2 metres in diameter, so the moment you put any shutter in there, you're really down to sort of almost going down there on a skateboard, so it's on your back. So so we're now looking at the in situ caisson method. I mentioned the safety benefits really limits the amount of people that need to be involved. We've achieved all the work that you've seen in the pictures here with a gang size between 8 and 15 people. It's only in the last 2 weeks that we've added another 8 to go to 24 hours. But what that means is we have small teams. We can have an open environment where everyone knows each other and everyone can challenge and talk about issues that we have. And that's really been a noticeable part of having a small team that's here. All of the design elements there all look incredibly simple, even in plan and in section. very easy to understand, and you'll find that the caisson structures have all gone exceptionally well because of the simplicity and all the hard work was kind of done in the design rather than leaving it to complex details at the site. So in terms of key learnings, certainly challenges with the mixed ground with the slurry TBM and the separation plant. I think we're over most of those now and hoping to finish next week, but understandably it's taken a little bit longer than maybe we envisaged originally. And then secondly, with all of these projects, we set aspirational levels for the likes of precast concrete, and I fully believe they're some of the best tunnel pipes ever produced in the UK. If you see them, but understandably, again, that took slightly longer than we might have imagined as well. But the product is worth it and will certainly last the 120 years that it's designed for. So, yeah, thank you very much.
So, evening, I'm Ed Lewis. I work on the central section of Tideway, and I'm going to be giving a bit of an overview on the main tunnel drives, some of the challenges, constraints, and finishing off with a bit of a progress update of where we are currently. So just starting off looking at the geological model, as Andy explained, Tideway is split into three sections, 3 construction contracts, west, central and east, geographically, but that also sort of follows the rough geology at the depth of the main tunnel. So you've got the western contract with a 7-kilometre drive in the London clay. The central section consists of a 5-kilometre drive heading west from the Kirtland Street site in the middle, up into the London clay, but launched from mixed ground in the sort of clay and Lambeth group, and a 7-kilometre drive heading east from Kirtland Street to Chambers Wharf, and again starting off in the same ground and then travelling down through the Lambeth group, Thanet Sands and into the chalk before Chambers Wharf. And the eastern contract is a 5.5-kilometre drive down through the chalk. If we just look at the Kirtland Street site in the middle, which is a double drive site, this shows the sort of geology observed during the SCL advances to construct the launch chambers. This is actually a few photos stitched together from the face logs during the SCL works, but it shows the mixed ground with the London clay in the crown, and then some of the upper layers of the Lambeth group lower down. So the TBMs on Tideway, there's 4 TBMs constructing the main tunnels, 3 earth pressure balance machines for the western contract and the 2 on central, with a slurry machine being used on the east. And just relating to the geology, you can see top left TBM Rachel, which is in the west, driving through the clay. Bottom right, TBM Millicent, which is being used on the western section of Central, again up through the clay. And then the other 2 pictures of Ursula, again on Central, but that's the machine that drives from Kirtland Street down through the Lambeth group and the more mixed ground. So you can just see the slightly more closed cut-to-head arrangement there with a lower opening ratio. So some of the constraints on site. All of the TBMs are being driven from shafts, which necessitates the need for an umbilical style launch, whereby the cut ahead of the machine and the first few gantries can be lowered down and start the excavation, with the remaining gantries and backup on the surface connected via umbilical hoses. The machine then progresses into the ground and as you create the space behind, obviously lowering the remaining gantries until you're at full configuration. Obviously, you've seen where we're working as well. All of the sites are in central London. So the bottom left just shows an aerial view of Kirtland Street back when we were setting up. And each of our main drive sites has an acoustic enclosure, which allows us to work 24/7 in close proximity to the sort of residents and the commercial properties nearby. Just looking in detail at the Kirtland Street site, which is the double drive site on Tideway. You can see the middle photo is a sort of detailed plan of detailed 3D model of the shaft just before setup. There's a lot of work went into modelling the systems, the conveyors, You've got the vertical conveyors, which take the spoil out of the shaft. And below, at the tunnelling level, you've got the sizers, cross conveyors, drive units, and the workings for the vertical belt loop take-ups in the shaft. So a very heavily congested shaft. And during this phase, and as a result of some of this sort of detailed modelling work, there were a few improvements made to sort of optimise the launch sequence and then tunnelling thereafter. One of them being the base slab was reduced and it was actually physically lowered by 6 metres. So a further excavation of the shaft, which allowed us to put the workings of the conveyors, the sizers and the cross conveyors below the deck to maximise the space available at working level, at sort of tunnel invert level in the shaft. And one of the other improvements was the launch adits that were created for the umbilical launch were increased in length to 37 metres each, which allowed a further gantry to be installed of the TBM, which allowed the initial launch to occur with the full configuration of the TBM conveyor installed. So, and Andy briefly went through the marine logistics and the commitments on Tideway. I just wanted to show what that meant for a site such as Kirtland Street. If you look at that in isolation, at peak production, we'll take away 4 muck barges, which is around 6,000 tonnes of spoil a day by river, and also bring in a segment barge that you can see there in the bottom right, which is 30 tunnel rings. That alone in a single day removes the need for over 250 HGV movements in central London. So, and that is just one drive site on its own, and you can multiply that across all of the drive sites and all of the CSO sites as well. Obviously, being in central London, we interface with a number of third-party assets. As you can see there as a summary, a few numbers: 75 bridges and 45 tunnels. One of the challenges of tunnelling directly underneath the river and following the course of the river is we've only got limited transects where we can actually monitor the performance of the TBM in terms of settlement and calculate the volume loss. So obviously, as general best practice, we through the SRGs and the daily review groups, we're constantly monitoring excavation rates against theoretical quantities, grout pressures and volumes, etc., and have that sort of constant loop between engineering, design and construction. To give an idea of the performance to date, this shows a volume loss calculation for an underground asset that we recently transited earlier this year. The black lower line shows the theoretical volume loss settlement that would have occurred for a 1% volume loss assumption, and then the red dotted line just shows the actual measurements observed, which equates to just under 0.3% volume loss, so quite impressive. I thought I'd just use this opportunity to raise this sort of one specific risk. I appreciate this has been discussed at the BTS before, but that's the risk of hypoxic ground, so deoxygenated ground gas, which can occur in the Up North Formation in the Lambeth Group. It occurs with the oxidation of an iron hydroxide, which is known as green rust, very often due to dewatering when air is brought into contact in the strata. And then the subsequent and recent recharge of aquifers in London can trap this hypoxic gas underneath the impermeable lower model beds, and obviously poses a future risk then to tunnelling and works that intercept that strata going forward. In terms of mitigation, I mean, I think the most important thing is having an understanding of the risk and knowing it's there, and obviously designing your systems to cope. Having a robust ventilation and monitoring strategy, and generally the sort of standard best practice measures in tunnelling, clear entry procedures, considered and tested emergency response systems, but also timing of work. So looking at when do you do interventions and avoiding sort of confined space works in these high risk areas. And to capture a few other health and safety best practices being employed on the project, I mentioned the use of the acoustic shed enclosures, but it does so much more than just keeps in the sound. It provides a sterile environment, day and night in terms of light, and obviously blocks out the weather throughout the day and throughout the year. And it also limits the impact on residents and third parties for light, noise and dust coming out of the shaft. There were a number of lessons learned on the TBMs on Crossrail. That was taken by the contractor and developed for the TBMs on NLE, and that register has further been taken and used by the whole team and the TBM manufacturers on Tideway. And part of the challenge now for Tideway is obviously the legacy and how we get those lessons learned out and make sure they're implemented on future projects. On the central section at least, we've been lucky with the continuity of labour and also the TBM manufacturer. Working in Kirtland Street, we're a stone's throw away from the Northern Line extension, and we're using a lot of the same labour, contractor and TBM manufacturer, and also retaining the TBM manufacturer staff for the duration of the drives. As I said before, we've used a lot of 3D modelling, including a virtual TBM, plans of the shaft, and we also carry out a detailed readiness review ahead of all major phases of works. Just to close with an update on where we are to date. Main Tunnel A, which is the tunnel in the west, commenced earlier this year with planned completion next year. Main Tunnel B has already completed, and you can see some stats on the right there in terms of the long average achieved, 15 metres a day, and some of the peak production. Main Tunnel C is now obviously the only tunnel in operation from Kirtland Street, with planned for completion August next year. And again, long average are currently around 16 metres a day, but with peak productivity, 54 metres a day and 262 metres in a week being the best to date. Main Tunnel D, which is the eastern contractor's tunnel, that in the chalk hasn't commenced yet, but that's due to commence in spring next year. And the link at the bottom of the page there, anyone can click on that and you can view the shot there and get real-time information on the current progress of the TBMs.
Okay, so I've just got a few very quick closing remarks. In terms of the project overall, we're just about 50% complete. We start commissioning towards the end of 2022 and to bring the whole system into service in April 2024 and hand it over to Thames Water to operate. So that's the kind of broad programme, and we're on track with our programme. We've had a lot of, obviously for this audience, a lot of discussion around the shafts and the tunnels. But the work where we're doing the connections to the Thames Water sewers they're major pieces of civil engineering in their own right. Some of these connection culverts, like the one at Deptford on the left, is essentially the same width as a 3-lane highway tunnel. So these are massive as well. Maybe that's the subject of another presentation in the future. But we can see the project really taking shape at ground level as well. Our focus for 2020 is obviously to complete the TBM drives that we're on at the moment, and the East team will be starting their TBM drives up, starting to mobilise for our secondary lining. So all of the tunnels have a primary precast segmental precast lining, primary lining, and then there's a secondary lining to go into those. So that'll be a key focus for next year, and continuing the work to intercept the Thames Water sewers. Obviously, we're looking at commencing the mechanical electrical work. It's reasonably simple, but it's pretty big scale and needs to be done right. And we're continuing to increase our focus on the completion, the commissioning, the handover phase, and making sure we're doing all the planning for that and all the way through. I think the project's in great shape, and I think that is very much because we've maintained a really strong focus on health, safety, well-being, quality, and sustainability. And if you get the things right, get those things right, then your schedule and your cost follow. So we've got to continue to maintain that focus. I mean, it's a privilege to lead this project in terms of delivery size. It's such a fantastic project, but we've got brilliant teams across all of the sites, and it's great to see the work that the teams are doing on every site. Obviously, we've seen 4 sites here, but there's 16 other sites could have given equally interesting presentations from equally excellent, capable, committed engineers. It's great to see the project developing, but it's also great to see the work that's going on with teams developing and getting experience of this, and you know, seeing the future of the industry develop on this project is just fantastic. Just like to acknowledge we've got some great contractors, as I said earlier, Balfour Beatty, Morgan Sindall, Balfour and Ban Nuttall in the west, Frovia Langerook in the centre, Costain Vonsi and Bashi in the east, and their consultants, Arapan Atkins and ACOM and MOTS, all doing great work. And I know there's hundreds of specialists who are doing work across the project, and we appreciate all the work that they're doing. Obviously, we're looking forward to finish the project and cleaning up the River Thames, and that's what our project's all around. But just for now, our focus is on keeping everyone safe till Christmas. So thank you very much for the chance to come and tell you about what we're doing.
Lee, you summed it up when you said your connection tunnel was relatively small at 3.9 metres. It's not small in my books. And we're becoming very blasé about the sheer size of structures that Tideway are constructing in the river. The photographs really don't do justice to the scale. But if you do get the opportunity to peer over the hoarding, I'd really recommend it. So we want a few questions now. And remember, the usual drill, name and affiliation. Can somebody take the microphones in just down here? And they're in the corner, down here, Charlie. In this corner, I think. So we've got some, oh, Mike, there we go, to start off with.
Mike McConnell, retired from Balfour Beatty. I think Andy and your team, UK Limited, you'll be very proud of what's happening here tonight. And I think that's one of the lasting impressions, that I think we're doing things here that can't be done that well elsewhere, I suspect. But it was just one point I'd just like to mention, and it's something that Ed brought up, and it was about the high-quality pipes from Enniskillen. Now, I couldn't think of a more remote part of the UK to actually bring in some work and try to fit it in, as it were, from Enniskillen. Now, these were concrete lined there. I'd just be interested to appreciate the length of these pipes, and was this sea fitted through Lough Erne into the Irish Sea and down, or you know, it's just good that a very remote part of the UK can actually be very competitive in this way.
Yeah, definitely. So Wardenburg are our major subcontractor we had in at Putney. So they have a relationship with Tracy Concrete in Enniskillen. They're doing a number of projects together with them, so they have that relationship there. So yeah, the pipes were 2.5 metres long. Obviously the composite lining was a fantastic win overall for us. In there, the quality's been good. They've also stepped up to the plate in terms of the quality requirements that we have as well, as a project of this size. So yeah, they were brought across by road on the ferry over to over and into the UK. They're in a holding yard in west of London, and then brought into site as required. So we can hold about 5 or 6 pipes on site at a time. So that's very much sort of just-in-time delivery kind of stuff. But yeah, very happy with the result. If that answers your question.
Next in the middle. Yeah.
Hi, David Giles, Langerook. I think it's a fantastic project. I had the good fortune to work at the Olympic Park around the Northern Outfall Sewer, so I got to see the old Bazalgette project, and a bit like the Olympics, this sort of project probably only come around every 100 years, so great for you to be able to work on it. My question is around the future proofing the project and the real-time monitoring that you might be installing in terms of the operation and maintenance in the future.
Yeah, I mean, from a civil engineering point of view, the system is designed for 120-year design life, and obviously a lot of thorough durability assessments. So I don't think there's any kind of embedded monitoring in terms of monitoring the asset. there is obviously a lot of monitoring around the control of the flows and level monitoring and flow monitoring and so on to control the actual system and to monitor the M&E kit. It's designed to have a 10-yearly inspection. So the work that we're doing there is the current design is to have access for vehicles for the personnel to inspect. The work that's going on is some research to look at, can you get an unmanned aerial vehicle or something similar that can do remote inspections in an explosive atmosphere, with remote control, no line of sight, and trying to get that to work. So that's the kind of, it's more of a how do you do the visual inspections in a remote way.
Hello, good evening. I'm Hasil from Warwick and the tunneling course. I have two questions, one from John and one from Ed. The first one from John, how did you determine the depth of your secant pile in the shotcrete section of your shaft, as well as the depth of your jet grout columns in that place?
Sorry, I didn't understand. How do we determine the depth of the secant piles?
Yeah, correct.
So that's purely geology. So we stopped just above the bottom of the London clay, and we're also pretty much at the limit of the piling rigs to install segmental casing. So that determined the 25 meters, and it just by pure fortune is half of the shaft depth. Then the second half in the sprayed concrete lining takes you through the granular strata, the Lambeth Group and Thanet Sands, and the base slab is located where it needs to be in relation to the tunnel, and the tunnel has a fall on it throughout the project for the sewerage to self-cleanse the tunnel. So that just the depth of the shaft is just where it needed to be geometrically by the design of the entire project.
And there was no termination criteria for those piles as such in terms of RPM or anchorage into the geology?
No, it was purely get those secant piles as deep as we can to minimise the amount of sprayed concrete lining that we needed to do, but we couldn't go any deeper because of the piling rigs and because of the geology. But the design is done so that the sprayed concrete lining will actually undermine the secant piles. So the secant piles are the primary lining of the shaft. There isn't any sprayed concrete lining over the top of them. We will bring a 1 metre thick secondary lining up the entire shaft, but the secant piles themselves are the primary lining.
Thank you. And my second question is to Ed. Once you're in Lambeth Group, you showed a photo that had a lot of varying strata in which you're using SCL. Now, what sort of TBM are you using for that? I understand from your presentation, are you using an EPB in that place?
Yeah, so both TBMs that launch from Kirtland Street are EPBs. And as I sort of briefly went through, the machine heading west sort of drives up into the London clay, so a slightly more open face. But the machine that drives down lower through that strata is a slightly more closed face, but both very similar machines, same manufacturer, and yeah, both EPB.
And the cutter consumption on either of them, I believe the variable strata would have more of that.
Sorry, can you say that again?
The cutter consumption? The tool consumption.
Tool consumption.
Yeah.
Yeah, obviously it's less abrasive in the clay, so there's a higher demand on tools, especially down through the Lambeth groups and some of the lower units where there's some quite abrasive ground. So there's a number of interventions, with a number of tool changes.
Thank you.
Damien McGettrick from Dublin Plant. I'm a Chartered Civil Engineer. It's a brilliant project. I've watched it closely for the last few years, and I think, obviously, congratulations on how you got on so far. Question is that the marine coffer dams are big structures, and do you sort of, some are staying in and some are coming out, I guess, because there's obviously some new public realm. Are they differently designed if they're staying in, if they're being temporary, and do you share that knowledge across all three sections, or do you sort of encourage the three different consortia to come up with their own solutions?
So the cofferdams that you're seeing are all temporary. So they'll all come out at the end of the project. That's part of the consent we have, is they have to be removed. So the permanent structures that are left are normally separated. So at Albert, we've got a piled wall, which we built up to form the permanent river wall. I think you've got something similar at Blackfriars. So certainly there is a lot of sharing of knowledge. Part of the project management team, I was in a program-wide role previously, and so we're part of sharing knowledge between the various contractors, and there are lessons learned and developed between each, definitely. Yeah.
Damien, it's one of the things I think the contractors have done a really good job on is sharing best practice, lessons learned. I mean, John chairs a tunnelling safety group, which has been fantastic at sharing people's thinking, planning, ideas from a health and safety point of view when things have gone well, or when there's been near misses. It's been really open sharing as to what the lessons learned are, and let's get it out to all the areas without any kind of criticism or anything like that. It's all been really positive to learn from. So I think that's something that's worked really well on the project.
One more question here on the left. How many more have we got? We're kind of running a bit short on time.
Kim West, Arup, thank you for a fantastic presentation, really interesting. The part that struck me was the caissons. They look to be enormous structures. If you could give us a sense of the weight of the caisson when it went down, and also the initial phase, my experience with very much smaller caissons is if you can get it going in the right direction to begin with, things go well. How do you control when you're pouring the concrete into the shutters that it doesn't settle while you're doing that?
Okay, so when we put in the cutting edge, part of that process was actually kind of having a temporary stopper slab underneath that, underneath the edge that you had there, because you had obviously the steel edge itself, and then a tapered concrete face underneath there as well. So there's a temporary slab within there. So in that initial phase, we effectively built the first couple of lifts. We also, within the rectangular, the cofferdam structure, we had a lower guide slab effectively, which with two cutouts for both of the caissons, and then we backfilled some of that cofferdam by about 3 or 4 meters, and then installed another slab. So effectively, you had dual slabs for that initial guidance. That helped us get through the first 2 or 3 meters of sand and gravel. And obviously, once you kind of sock it into the clay, there's only so far then you kind of deviate from that point. So yeah, it was kind of a slow and steady to get the first ones going. We got ourselves the two guide slabs in. Then we broke out that temporary slab, and then we started the drop. In different strata, I think that Wardenburg have worked in projects where it has settled fairly significantly during the pour in softer ground. We had only very small movements in the order of sort of 20 to 50 mil during a pour, which is manageable as long as you account for that in any shuttering clearance that you have with your upper collar. So that was successful, and yeah, there's definitely a valid risk, but given the competency of the clay, it was quite minimal.
And roughly how heavy was the whole caisson?
I haven't got that number to mind, but I think the shaft was around a meter. The shaft was 700 millimeters thick, and the caisson was almost a meter. So quite significant structures. There was the potential for stuff to get stuck as well. We did plan to have some sort of backup Kentledge available, but that was never required. Once you get past a certain point, you're looking at over thousands of tons. So it didn't need much encouragement on the way down.
Thank you.
Do we have one more question on the right there? Oh, Neil, yeah, at the front. I'm going to have to cut it after you, Neil. Good.
Neil Moss, Transport for London. Very simple question. There's a huge difference between the progress rates for the TBM drives 16 metres was the average, 54 metres was the best at the moment. That's a huge range.
Yeah, it is a large range, but bearing in mind, you know, you going through an umbilical launch is a slow process. That dramatically alters your average production rates. With one machine in the ground and then launching a second machine, you're obviously limited on your progress until you've got full configuration of both machines, and we've got a double track configuration for the locomotives at pit bottom. Further to that, you've got interventions. As you said, some of the highly abrasive grounds in the Lambeth group require full tool changes, installing California crossings in the tunnel, conveyor boosters to reduce the sort of tension in the belts. That brings the long average down. So whereby on good days we might be installing sort of 20 to 30 rings, you know, we can't maintain that continuously with constant stoppages, you know, and planned stoppages for belt extensions, service extensions, and then the inevitable interventions and another unforeseen downtime. And obviously there's a number of restrictions. We're bound by the tides at certain times when we can muck away with two large TBMs working out of one shaft and a limited muck bay in central London. There are restrictions when your progress has to be sort of drawn back. So yeah, there's some very good days, but unfortunately we can't maintain that 365 days a year.
So what is the long average that you're aiming for?
I think the planned long average at the start of each drive was 10.5 rings on one drive and 11 on the other, which equates to about 18, 19 metres a day. So the first TBM that's finished was just below that, but as I said, that had the stoppages for the launch of the second machine, and now we're in sort of full production mode on TBMC with TBMB already complete. Obviously those logistical constraints are reduced with only one TBM running, which is why we've got better rates now showing on that drive. So we'd be looking to sort of hit the planned long average on that, which would be around 18 metres a day.
Thank you.
Okay, so could we have one final cheer for Andy Alder's Jamboree, please? I'm afraid I've got rather a lot of chair slides, but I won't dilly and dally around too much. Thursday the 16th of January, get those Christmas jumpers on for our first meeting in the new year, a feast of Norwegian tunnelling, cities and fields. Ian, I know what your Christmas present is going to be now. Willie, I know you've already got a Christmas jumper. And just to show you that we know what we're talking about and where Norway is, I've added two maps, one of a city and one of a field. Meeting in February, a joint meeting with MinSouth, the West Cumbria Mining Project. And then moving on to the 13th of March, the British Tunnelling Society Young Members Conference 2020, calling for presentations and sponsors. Excellent value, held yet again at Arup in Fitzrovia. You've seen these stories. We ran them for a few minutes before the start. Two here, one written by Neville Harrison and one by Roy Slocum. Thank you for those stories. And then another story by Sam Simons. A very big thank you to those three authors. However, the membership appears to be slow at writing. Please don't be shy. Pick up your pens. There are a few up here on the front console if you're running short of pens. Christmas is coming as well, so please put pens to paper. So Ken Spivey, of course, who we must congratulate for the well-deserved award of being Tunnel Supremo, has put together a few pie diagrams that even I understand. So to illustrate how shy you are about writing, so far we've only received 45 stories, that's 7% of the membership. I won't ask for a hand count in here as to how many have written stories, but it's not so good. Christmas is coming. And another pie diagram telling us, in essence, that we need another 128 stories. So I am beginning to understand pie diagrams, Ken, and thank you very much for them. But then just to really hit us home, Ken provides a programme. We all understand programmes. Yeah. And most of us contractors understand them because we're usually behind programme. So this is a programme showing that the last story submission is in February. So come on, you great writers. Christmas is coming. Pick up those pens. And look, again, if anybody needs a pen, there's one up here. But we are, be noted, be turning to bribery and corruption. So for January only, we'll be introducing the story sausage. Write and submit a story by Friday the 10th of January, and we will send you a voucher to you for a sausage story that will be added to your meal on Thursday the 16th of January. So Ian, you will cut a great dash in your Christmas jumper eating your sausage story. Don't be jealous of Willie. Better than a Blue Peter badge, but hurry, the offer only applies while stocks last. So look at our website for inspiration. Look at our website for inspiration. There's lots of bullet points here. I'll click through. You can look at that. Photographs. You know we are a people business. So please, if you're submitting a photograph, remind us of who we're looking at. But plenty of photographs. And I know you received some photographs today, Ken, wherever you are. Yeah, you have received photographs today, Ken. Yes. So now, how to claim your free sausage story? Get writing. And if you want to log on to the website, BTS, British Tunnelling Society website, there is a logo to follow the sausage. Where am I clicking? I'm going the wrong blinking way here, aren't I? So, BTS at 50. Remember that deadline. Friday the 10th of January to claim your free sausage story. And yes, for those shy corporate tunnellers who don't actually want to write a story, we're still looking for sponsorship. So hands in pockets for Christmas. Further dates in the diary, 6th to 10th of July, our tunnelling course at Warwick. Mid-January, we are developing a tunnelling podcast in association with Reby Media. The tunnelling podcast will celebrate the work of tunnellers who use ingenuity, practicality, science, theory, and determination to build a better world. So if you don't understand any of those words, or don't understand, like me, what a podcast is, you've got Christmas to find out. Our blog, if after writing your story you want to chew over some of the tolerances within our specification, log into the blog and give us your views. Neil and Neil's address there if you don't know what a blog is. Apprenticeships, and we're getting a new cohort in 2020. If you are interested in the apprenticeship scheme, please get in touch with Abby Pearson. And then, not quite finally, but almost finally, a very big thank you to you, Andy, for putting together a fantastic meeting tonight and inspiring all those young Turks to speak out. And of course, for you and for Jacobs for sponsoring the bar and the sausage and chips. And finally, one final thing, to wish you a very happy Christmas from the Tally Hut. The bar is open.